In today's video, I am going to explain the differential equations reducible to linear differential equation. A differential equation of the form dy upon dx plus py is equal to q y raised to the power n, where p and q are some functions of x or constants, is the differential equation which can be reduced to linear differential equation. Obviously, this is not standard linear differential equation, because in linear differential equation there must be only a function of x on the right hand side, which is denoted by q, but here y raised to the power n is extra. So if this is not here, it is perfectly a linear differential equation, but because of y raised to the power n, this is not a linear differential equation but can be reduced to. This equation is also known as Bernoulli's equation. So what is the algorithm to reduce a Bernoulli's equation? Now we are going to discuss the method by which Bernoulli's differential equation can be reduced to a linear differential equation. So step 1. In step 1, we need to divide the whole equation by y raised to the power n. Divide both sides by y raised to the power n. So we get 1 upon y raised to the power n dy upon dx, plus if we divide this term by y raised to the power n, 1 power is reduced from the denominator and we get p into 1 upon y raised to the power n minus 1 is equal to, on the right hand side, if we divide this term by y raised to the power n, obviously q is left. So we get this form of an equation. In step 2, we need to assume this expression, that is 1 upon y raised to the power n minus 1, as some other arbitrary variable, say u, v, w, whatever you may consider. I am taking z, and let it be equation number 2. We may write it as y raised to the power 1 minus n is equal to z. Then we have to differentiate it with respect to x. By chain rule, we have to differentiate both sides because we are differentiating with respect to y, but we have two variables y and z which are assumed to be functions of x. So we get 1 minus n y raised to the power 1 minus n minus 1 dy upon dx is equal to dz upon dx. This positive 1 and negative 1 cancelled, and we are left with 1 minus n y raised to the power minus n dy upon dx is equal to dz upon dx. Now we have to transpose 1 minus n to right hand side. We get y raised to the power minus n dy upon dx, and obviously y raised to the power minus n may also be written as 1 upon y raised to the power n. So simply we may write it as 1 upon y raised to the power n dy upon dx is equal to, transposing this expression, we get 1 upon 1 minus n dz upon dx. Let it be equation number 3. Now step 3. In step 3, we have to replace 1 upon y raised to the power n dy upon dx by this expression 1 upon 1 minus n dz upon dx in equation number 1, and we have to replace 1 upon y raised to the power n as z because we have assumed in equation number 2. So here we write z, and because of this substitution 1 upon y raised to the power dx upon dy is changed to 1 upon 1 minus n dz upon dx. So using equation number 1, 2, 3, we get 1 upon 1 minus n dz upon dx in place of this expression. From equation number 3 we have substituted this. After that plus p is there, and 1 upon y raised to the power n minus 1 is assumed as z. So from equation number 2, here we write z, on the right hand side only q. After that we have to multiply both sides of this equation by this expression 1 minus n. So we may write this equation as dz upon dx plus 1 minus n p z is equal to 1 minus n q. Clearly, this equation is a linear differential equation which can be solved easily by the method we have discussed in the previous video. Now let us take an example. Example 1. Solve dy upon dx plus y upon x is equal to y square upon x square. So obviously this is not a linear differential equation because of this y square on the right hand side. So this is a Bernoulli's differential equation. Now we have to divide both sides of this equation by y square. So we get 1 upon y square dy upon dx plus 1 upon x into 1 upon y, because if we divide this term by y square we get 1 upon y is equal to, and here on the right hand side only 1 upon x square is left. In the next step, what we have to do, we have to consider this expression as z. Let 1 upon y is equal to z. So let it be equation number 1 and let it be equation number 2. This may also be written as y raised to the power minus 1 is equal to dz. So if we differentiate this equation with respect to x, by chain rule we get minus 1 y raised to the power minus 2 dy upon dx is equal to dz upon dx. This may be written as minus 1 upon y square, because y raised to the power minus 2 may be written as 1 upon y square dy upon dx is equal to dz upon dx. Now transposing this minus 1 to right hand side, we get 1 upon y square dy upon dx is equal to minus dz upon dx, and let it be equation number 3. Now from equation number 1, 2 and 3, we have to replace 1 upon y square dy upon dx from equation number 3 by minus dz upon dx. So here we get minus dz upon dx plus, and we have assumed 1 upon y as z, so here we get z 1 upon x z is equal to, on the right hand side, 1 upon x square as it is. So now multiplying both sides by minus 1 to eliminate this minus sign, we get dz upon dx minus 1 upon xz is equal to minus 1 upon x square. Let it be equation number 4, which is perfectly a linear differential equation. Now we have to proceed in the same way as we have done in the case of linear differential equation. So comparing with dz upon dx plus pz is equal to q, we get minus 1 upon x as p and minus 1 upon x square as q. Let it be equation number 5. Collectively we have written both the equations as equation number 5. So now integrating factor e raised to the power integral p dx is equal to e raised to power integral p is minus 1 upon x dx. So we get e raised to the power minus log x, which may also be written as e raised to the power log x raised to the power minus 1. So we get only x raised to the power minus 1 because e raised to power log eliminates each other, is equal to 1 upon x. So integrating factor we get 1 upon x. Now proceeding from this step, substituting the values of integrating factor and q, integrating factor and q in the equation, z into integrating factor is equal to integral q into integrating factor dx plus c. And be careful, there should be z instead of y because linear differential equation is the form dz upon dx plus pz is equal to q instead of dy upon dx plus py is equal to q. So variable is changed now. So in place of y we get z over there. So this is the equation in which we have to substitute integrating factor and q. So integrating factor we have calculated as 1 upon x. So z into 1 upon x is equal to integral, and q is equal to minus 1 upon x square from equation number 5. So minus 1 upon x square into integrating factor 1 upon x dx plus c. So this may be written as minus should be taken out, and x square into x cube, so 1 upon x cube dx plus c. So minus integral, this may be written as x raised to the power minus 3 dx plus c. So integrating this we get minus x raised to the power minus 2 upon minus 2 plus c. So these two minus becomes plus, and ultimately we get x raised to the power minus 2 plus upon 2 plus c, x raised to power minus 2 upon 2 plus c. And obviously x raised to power minus 2 may be written as 1 upon x square, so we may write it as 1 upon 2x square plus c. Finally we have to transpose 1 upon x to right hand side, so it will multiply both the terms, and we get z is equal to x into 1 upon 2x square plus x into c. So here x will cancel one part from denominator, and we get z is equal to 1 upon 2x plus cx. Now let it be equation number 6. Why we have written equation number 6? Because this is in terms of z and x, and z is a variable assumed by us. As we have discussed earlier, the final answer should be given in the same variables given in the sum, and in the sum the variables were x and y. So the final answer should be given in x and y. So what we have to do? Simply we have to write z as 1 upon y from equation number 2 in this result. So from equation 2 z is equal to 1 upon y. Thus replacing z by 1 upon y, we get 1 upon y is equal to 1 upon 2x plus cx. So this is the required solution of the differential equation. Bernoulli's equation is not only the differential equation which can be reduced to linear differential form, but there is a second form also which can also be reduced to linear differential form, and that is f dash y dy upon dx plus gx fy is equal to phi x. That means a differential equation in which the coefficient function of dy upon dx must be differential of the function of y, which is a multiple of a function of x, and on the right hand side there should be only a function of x. So differential equation of this form, f dash y dy upon dx plus gx fy is equal to phi x. Let us take an example to understand this form. Suppose this is a differential equation to be solved. Tan y dy upon dx plus tan x is equal to cos y cos square x. If we observe, there is two functions on right hand side. One function is of x and other function is of y. So to make right hand side only a function of x like phi x, we need to transpose cos y from right hand side to left hand side, so it will divide both the terms. So we may write it as tan y upon cos y by dividing both sides by cos y, dy upon dx plus tan x 1 upon cos y is equal to cos square x. As we know well, 1 upon cos y can be written as sec y, so sec y into tan y dy upon dx plus tan x into sec y is equal to cos square x. Now it has turned out to be the same format. There is a function in the multiple of dy upon dx which is sec y tan y, which is exactly differential coefficient of sec y, which is multiple of a function of x like gx into fy, and on the right hand side there is only a function of x like phi x. So what to do in this? In this, first we have to assume, in first step we assume this function of y, that means in standard form we can say fy should be assumed as z. Sec y is equal to z. It implies that if we differentiate both sides by with respect to x, we get left hand side, the differential of sec y will be sec y into tan y into dy upon dx by chain rule, and on the right hand side differential of z is dz upon dx. So if we replace sec y by z here in this equation, we need to replace sec y tan y dy upon dx by dz upon dx. Dz upon dx, and after that plus tan x, and sec y we have assumed z is equal to cos square x, and obviously this is a linear differential form, so we have to proceed it in the same way as we have discussed in the case of linear differential equation. We have to compare this by dz upon dx plus pz is equal to q. Then we have to find out integrating factor e raised to the power p dx, and then we have to substitute the value of integrating factor and q in the equation. Z into integrating factor is equal to integral q into integrating factor dx plus c. So you may proceed as you might have done in the case of linear differential equation. As I have created a dedicated video for linear differential equations, so I'm not going to explain it in details. You can try yourself. So there are only these two forms which can be reduced to linear differential form. One is Bernoulli's equation and other one is this equation, f dash y dy upon dx plus gx into fy is equal to phi x.